afternoon and welcome to the Crop Down Studio. My name is Emma and we are delighted to be hosting a crop special of our show tonight with our contestants Michal and Elliot. Over in Dictionary Corner we have Chloe and David, and of course we have Elise on the numbers. Our first round will be the maths round, where we will be looking at agricultural mathematical models where the contestants will need to take into account the consequences that different population densities have on the growth of crops and the ability to maintain a sustainable and efficient supply of crops. So, the problem is as follows. Create a mathematical model to describe the yield of a crop at any time during the period from planting to harvest and find the optimum yield. To guide you on this problem, you have a set of data in front of you and you will need to take into account the effect of yield on differing numbers of plants per area for crops commonly harvested within the UK. Your models will need to be able to be validated by Dictionary Corner. Crop Down. Okay, and time's up. Has anyone got any solutions?
No, I couldn't get one. I only got so far. I think I'm on the right tracks, but I don't know where to go from now.
So Michal, would you like to explain where you've got to?
We start by outlining the variables. So N is the number of crops, Y is the yield, W is the weights, capital Y is the carrying capacity, and K is the constant of growth. Assuming the yield increases at a linear rate with time, we get dy by dt is the constant of growth times by the yield. We note that as the yield tends to carrying capacity, the rate of growth tends to 0, and by moving all the variables to one side, we get 1 over the yield multiplied by 1 take away carrying capacity divided by the yield. Dy by dt equals the constant of growth. Expand the brackets and simplifying, we get the resulting expression where I ran out of time.
So Michal was going in the right direction, so starting from where he left off, which was this line here, we can separate the variables in order to provide something that we can integrate. Integrating that, we get this line here, and through the laws of logs, we can combine our logarithms here, and as a result of the fact that a is just a constant, we can take out a factor of k, leaving t plus b in the brackets here. Next we can take everything to the power of e, which leaves us just with y over big Y minus y on this side, and e to the power of k t plus b on this side. Through multiplying this out and then taking all of the positive terms onto one side, we can then get this line here, which gives us all of the little y terms on one side and the big Y terms on another side. So taking out a factor of y here, we can take this term here, which allows us to have y on its own, which is what we were integrating with respect to. Then multiplying through by a factor of e to the negative k t plus b, we can simplify it to form this. We only have one use of the exponential function here. And as a result of the way we want our model to work, we would prefer to have a negative constant here. So as a result of the fact it's just a constant, we can change plus b to minus c, leaving us with a general solution.
Dictionary Corner, how can you validate these results?
Thank you, Elise, for the general solution of the logistic function.
Right, now it is essential that our model is validated. This was done through using the given data of a barley yield and changing the variables in our model to make the curve follow closely to the pattern of our data for all the various plant sizes. Using a graphing technique called Desmos, we found some variables that fitted our data.
To validate our model, first we plotted the given data for each different number of plants per plot. We then used the logistic function to closely follow each of our data sets. We set capital Y to where the carrying capacity is met. We then set C to 4.3 for all data sets, so that we could change K, the constant of growth, to follow the data. From the data we observe that the optimum number of plants per given area is 32 plants. This had the joint highest constant of growth and also had a carrying capacity that wasn't that much less than the others, which had more plants per given area. so we believe that this is the most efficient amount of plant to plant in a given area.
It's now time for an advert break, but please enjoy the on-screen conundrum.